of light in general. So thank you for accepting the invitation, for coming here to Brazil, and welcome to Brazil, to São Paulo. Okay, thank you.
So thank you very much for a nice introduction. And first of all, I would definitely like to thank for this very nice event and for having me here. Okay, I'm experimental physicist. We sit in Olomouc, more or less in the middle of Europe. And you can find about what we do on our website. But quick sneak peek, let's say, we explore wave-particle duality and manipulate light coherently as well as at the level of adding and subtracting single photons. For example, this experiment you can see here is our last or very recent result on coherently adding several photons, up to 3 photons, to quantum state of light, and using these highly non-classical states for noiseless quantum amplification. So another area of our research is characterization or detection of quantum states and their metrology. And this will be actually the topic of the lecture today. So we start with quantum state tomography as a way how to characterize the quantum states. Today we introduce the basic concepts and overview recent results. I would like to give you some hints what is interesting in this field, and for example, when you continue in research in this direction. And next lecture on Thursday, we will make a detailed tutorial on application of one-particle methods for quantum state reconstruction, maximum likelihood, statistical method, including implementation details, Python codes, everything. But today we will stay at the sort of general level and focus more on the new results. We will mention the importance of regularization, especially for underdetermined problems, and demonstrate this on photon number resolving detection as a nice application and very important task in quantum science and technology. Next, we will continue with analyzing or answering the question, what is the ultimate precision limit of quantum measurement? So what is the smallest error we can reach? And in connection with this, we will introduce heavily multi-projection measurements and measurements with random projections, and apply this for some advanced sensors of light in our case. And finally, maybe probably the next lecture, we will discuss the case where we either don't have the full information or we simply don't need the full quantum state reconstruction. We don't need the full information about the quantum states. We are interested only in some particle quantum features, which could be entropy of the subsystem, quantum entanglement, and so on. And we will discuss how to proceed with extracting these features from incomplete data. The final point will be the discussion of universality or device independence of these detection models or systems. And we will demonstrate this on a problem of super resolution of single emitters. So basically in imaging, so in some sense we cover basically everything from highly quantum entangled systems to image reconstruction, but everything will be somehow connected with the principal question, what we can learn about the physical system given some imperfect, finite, limited data. And okay, I will be here, of course, today afternoon, tomorrow afternoon. So if you have any question, I mean, within this area, I would be extremely happy to discuss with you. Some of the application or measurement schemes I will present you today will somehow contain or will be connected with machine learning. And this is a very hot topic, especially after the last week Nobel Prize. We probably can't say here or discuss here if machine learning is enough sort of physics to be awarded by Physics Nobel Prize. But what is, I mean, for sure is that several concepts in machine learning have been sort of influenced by the physics and vice versa. Definitely, in many physics applications, we use and we have used successfully concept of machine learning or deep learning. Especially, I mean, generally in physics, but particularly we are now interested in quantum science and technology, and machine learning is very useful in extracting structures, in extracting information from real measurement data. It has also been used for optimal optimal control of quantum devices. So basically designing the classical control signals for controlling the quantum devices. Even we can use machine learning to develop, to invent new quantum devices or states, which will not be covered here today, but I mean, there is a huge topic about this. And finally, of course, the more or less the original application, the first application, I mean, real-world application of neural networks, for example, of machine learning, is definitely the field of imaging. And I mean, in quantum technology and science, we will be interested in imaging of single emitters, single point-like sources, which has very nice applications in our field. I mean, we are physicists, so it's very, very important not to just use blindly any hot topic sort of methodology and apply for our problems, but also discuss limits of these methods, interpretation of these methods. And this is especially important for machine learning, which tends to be sort of like black box. You basically have a large model, then apply the data, get something, and yeah, okay, what now? So in physics, we should definitely, and quantum physics, we should definitely discuss scalability of machine learning models, because we know that the dimension of physical systems, the Hilbert space, grows exponentially with the number of particles or parties. And we are interested how machine learning model can handle this. Definitely we should discuss device or even dimensional independence. I mean, we definitely don't want to train a a model for this system and that system, for this measurement and that measurement, and basically have a huge pile of specific models which address very specific problems. It would be much nicer to have more sort of universal model which can work for arbitrary measurement, for example, or it can work for 2 qubits in the same way as for 8 qubits without retraining. I mean, yeah, maybe this is a little bit science fiction now, but at least we should try to go this direction. The detailed introduction to machine learning, or even machine learning in physics, is definitely beyond the scope of this lecture, unfortunately. But I can definitely suggest some very nice reviews, recent reviews of machine learning for physics. And if you would like to start with machine learning, and especially deep neural networks, for your sort of physics research, then definitely I would suggest online courses of Florian Marquardt. Maybe you probably know these courses. Florian is a physicist, and these courses are really tailored for physicists as a first step to machine learning. They are on YouTube, but also on Florian's webpage, with other materials and doubts and updates. Okay, let's start with some physics. So basically everything will be somehow connected with quantum measurement, and particularly with quantum state reconstruction using quantum tomography, so using some multi-projection measurements. So the basic sort of workflow for this problem is as follows. We have some unknown quantum state which we would like to characterize. This quantum state is measured by multi-projection, multi-component measurement. It can be really something which multiplexes the states and have multiple sort of light bulbs. And if you click at this light bulb, then you know that this particular measurement output was realized. It can also be the time sequence of measurement. Doesn't matter. This is generic description. To have some idea what we can have as a quantum measurement, M. For single qubit, for example, it can be the minimum symmetric informational complete measurement consisting of only 4 projections, basically lying an tetrahedron inside a Bloch sphere of the single qubit. Also, very known measurement is, for example, Pauli measurement, 6-component measurement containing or consisting of projection to 6 eigenvalues of Pauli matrices. This is very often measurement scheme used across quantum physics with various implementations, various physical systems. For 2 qubits, similarly, we can have, for example, these local Pauli measurements. So each qubit is subject to measurement with these 6 measurements. For example, for 2-photon entangled state, we have 2 photons. 1 photon is measured by projecting it to horizontal, vertical, diagonal, anti-diagonal, and circular polarizations. The second photon's same, and we measure all the combination between these projections. So overall, we have 36 measurements for 2-qubit system. There are, of course, other measurement systems, for example, already mentioned symmetric information complete measurement or mutual unbiased basis measurement, but these are not local for a higher number of qubits. So basically, it contains measurement projections where we project to entangled state, and this is definitely for experimentalists a little bit nightmare. It's much more complicated than local measurement schemes. So we will keep more on the side of local measurements, which is always much more feasible. So having a known quantum state and defined measurement, we can apply Born rule, basically evaluating the theoretical probabilities, the probabilities of the individual measurement outputs. It's simply the linear relation. It's a trace of product of the density operator of the quantum state and the operators of the individual measurement outputs. These are our ideal probabilities, and now we have to measure. We have to really perform the measurement. And we get the measurement data, which unfortunately are not equal to ideal probabilities. It would be the case only if we repeat the experiment infinitely many times, which is not possible. So with a finite number of state copies, finite number of measurement runs, we have something. We have basically only samples from the ideal probability distribution, and it means the measurement data are not equal to ideal probabilities. This is important fact. And question now is how to get the original sort of measured quantum state with the lowest possible error based only on the measurement data we have. And very nice sort of toy model for quantum state reconstruction or estimation is just a direct inversion of something we get with one single assumption. If we assume that the measurement data are same as the ideal probabilities, which are not, but if we assume this, we get similar, a simple system of linear equations. And I mean, these are data. This is the description of measurement device, and X stands for parameters of the unknown quantum state. So now, if we are able to compute an inverse matrix, we can apply to data. We have the description of our quantum system, of our quantum state. This is by far the worst method we can use because first, it's based on the wrong assumption. Second, we know that matrix inverse, especially if the system is not perfectly determined and so on, it's prone to noise amplification and instabilities and so on. And also, there are no constraints. Where are our constraints to have normalized state and positive states? They are not there, so basically what we get from this method is probably some object, some matrix, but definitely it's not guaranteed to be a proper quantum state. So instead of this, we can use some more advanced statistical methods. We will discuss maximum likelihood later, so just two notes. Here, we don't assume the equality between probabilities and relative frequencies between data. We search for quantum state which is most compatible with our data. But that's all. And we can include our constraints on quantum states. So it's much better, but definitely it's, okay, sorry. One note, important note. I will talk basically only about quantum states or quantum state characterization in the whole lecture. But there is a very interesting theoretical concept called Choya-Miłkowski isomorphism. And this basically shows that quantum device, or the mathematical description of quantum processes, quantum devices, is equivalent to description of quantum states only on larger dimension. For example, one simple example, if we have a single qubit channel operation, so basically mapping from a single qubit to another single qubit, then this quantum channel is described by a sort of object which has same properties as density matrix 4 times 4, so basically density matrix of 2 qubits. So when we learn how to characterize, how to reconstruct a quantum state, we at the same time know how to reconstruct quantum processes or devices. Okay, so back to the methods like direct inverse and maximum likelihood. Of course, we have many other methods. We have Bayesian methods, we have semi-definite programming as a subset of convex optimization, many other methods for exact full quantum state tomography. Unfortunately, all these methods, I mean, the quantum tomography itself requires some minimum number of measurement projections, some measurement outputs. We call this minimum number quorum, and very unfortunately, this quorum increases exponentially with the dimension of the system, with the number of qubits. So we have really scaling issues. This is actually the reason why full quantum state characterization, full quantum state tomography was performed at maximum for 12, 14, maybe particles or parties, photons or atoms and so on. And actually, it was not a maximum likelihood. It was direct inverse, maybe somehow corrected to give physical results, but maximum likelihood or other statistical methods are quite slow. I mean, we can't image to apply something like this for 100 qubit systems. We actually can't imagine to even take a data for such a full tomography. So this is exactly the reason why many approximative methods were developed. And it's important to know one thing. If we use some approximative method, it always assumes something about the structure of the state, about the symmetries in the state. There are assumptions, and it means there is a bias. So, for example, compressive sensing uses some sort of very simply said sort of regularization using L1 norm. Typically, it tends to more sparse solutions. And it means, of course, if our state actually is not sparse, we definitely make some bias and shift the reconstructed state somewhere in different direction than the original state was. And same with other methods. For example, matrix product state, extremely useful method, especially for many particle systems But again, it assumes some inner structure of the quantum state description, and as a result, it really struggles with long distance, long scale entanglement. So these methods are useful, but we have to know what is behind. And finally, of course, machine learning was used, typically neural networks for characterization of quantum states. Either we have some deep neural network which inputs experimental data and outputs the predicted quantum state. This is sort of quite straightforward method. Or, and this is actually the original way how neural networks were introduced to quantum state characterization and characterization of many body systems, actually. And these are neural network quantum states, where the neural network itself plays a role of quantum state. It's basically an approximation of the quantum state. Originally, restricted Boltzmann machines were used for this, but now routinely also we use deep neural networks. So, what do we have now? Big picture. We definitely need more measurement outputs. We need multi-projection measurement to observe our system from different sides, from different angles, because otherwise we can't see all the structure in. And the second thing, and this is a little bit different from classical systems, in quantum realm, we have to repeat the measurement several times. We need to use several copies of the quantum state. So we need some quantum resources because of the detection statistics. And this slide will be sort of our crossroad for the rest of the lecture, because we now discuss different cases. And the first case is the case where the number of projections, measurement projections, is smaller than the quorum, smaller than what we need for exact, precise quantum state reconstruction. So, again, a very nice insight we can get from the simple direct inversion, where now we have a smaller number of equations than the number of variables, which means, I mean, to have simple visual idea, let's say we have only 2-parameter quantum state, so we have only 2 parameters, x1, x2. We have only one Born rule equation, so only one data, sort of one data point. And of course, I mean, the solution now is not unique. We have all hyperplane, in this case a line within the 2-dimensional plane, containing all solutions, all same, the solution of the same sort of possibility. So how to choose one unique particular solution? We can't, at least we can't without some other additional information, some, let's say, we call it regularization. For example, we may want that our solution will be compatible with our data, so it lies on the line, but at the same time, it's the smallest possible solution with the smallest possible variant, with the smallest possible values of x1 and x2, I mean on average. And of course, this means that we are looking at a solution which has the smallest distance, Euclidean distance from the origin, so basically the cross-section between our line and the circle. the smallest possible circle. So now we have our unique solution, but of course there is a bias. Based on the assumption we were looking for the solution with the smallest variance. And of course, this regularization can be chosen ad hoc. So we can take different norm, for example, L1 norm, which gives us the most sparse solution, as we already mentioned. There are lots of other ways how to do. For example, we can search for least informational rich solution, and we can employ the regularization using maximum entropy, and so on. But again, the problem is that assumption always, this additional prior information always means some bias. And we will show in the next example, physical example, that actually we can use as a benefit, because sometimes the measurement schemes itself have some inherent bias. And we can use this additional regularization to counter interact the original bias and make the whole system, the whole reconstruction less biased. This example is counting single photons. I mean, let's say we have optical pulses, they contain different number of photons, and of course it means we have some photon statistics. If we can measure, if we can project to ideal Fock states, so to states with precisely defined number of photons, like if we can project a state with exactly 0 photon, exactly 1 photon, 2 photons, and so on, we can build the whole photon distribution, and we know everything about this degree of freedom of light. Unfortunately, this is not possible, and not just because of technical issues, but mainly because the Fock state basis is infinitely large, and we can't have the measurement device with infinitely many detection outputs. Plus, of course, there are other issues like efficiency and crosstalk between detection channels and so on and so on. So is it even important? I mean, if we will try to make a photon number detection at least in approximative way, there are applications for this. Definitely, yes. I mean, this is probably the most sort of quantum detection performed across many applications. It ranges, I mean, the application of photon counting and evaluating the number of photons and their correlations. It ranges from measuring the angular diameter of stars using stellar interferometers, down to counting and localizing single molecules in single molecule microscopy. And of course, in quantum optics, also, I mean, is the fundamental way, actually, how we define the classical, non-classical, and, for example, non-Gaussian states. So it's really important to know how many photons we have in our state. And how this is done, how we can do this, at least approximately. The basic model for this is using some detectors we have because photon number resolving detectors, we don't have them. So what we have are single photon detectors. the name is similar, but the performance is completely different. A single photon detector can't resolve number of photons, so it can resolve 2 and 3 photons, for example. What it can distinguish is the darkness, so basically 0 photon, or light, so 1 and more photons. Here, there are the simplest measurement operators describing such a single photon detector, but really, I mean, under ideal conditions, without losses, without noise, and so on. But it's enough for us to have the basic idea. Anyway, if we take our multiphoton state and multiplex it to many, divide it to many single photon detectors, and there are lots of them, more than photons in our state, it's very small probability, there is very small probability that more than one photon hits a particular single photon detector. And it means it gives correct result because there is either 0 or 1 photon. So we basically make a dilution of a photon stream and use many single photon detectors. Now, of course, we can have electronic outputs, at least from the detectors which click, and we can build a energy spectrum and the histogram of detection clicks. Okay, this is the basic idea how to do it experimentally. I mean, I will reduce the number of experimental stuff during this lecture to bare minimum, but let's say at least a few things. We can multiplex optical signal in spatial domain or in temporal domain, in time. And I mean, there are different benefits of doing this. For example, we can typically have lower losses for spatial multiplexing. On the other hand, we have slightly higher losses in time multiplexing, but it's more efficient sort of detector-wise. We need only we need only 1 or let's say 2 single photon detectors instead of, for example, spatial multiplexing, then where we really need the whole array of them. Okay, sorry. There are also detectors with inherent photon number resolving detection. Typically, they are based on superconducting thermometers, sort of. And again, if we look at their energy spectrum, we can see that there are some resolution between 0, 1, and so on photons. But actually, you can see that there is a massive crosstalk between the detection channels. And we can go, let's say, to even with very careful fitting, we can go, let's say, somewhere around 20 or maybe 30 detection channels, so 30 photons, which we can resolve. With spatial or time multiplexing, we have very nicely resolved energy spectrum, but we are typically limited in the number of channels. And the question, of course, is how far we can go. So again, a very quick sneak peek. This is a 20-channel photon number resolving detector we have in our lab based on spatial multiplexing. It's fully reconfigurable and so on. We also implemented time multiplexing using fast electro-optic switch and low-loss delay line. And with reasonable losses, we can go, let's say, up to 12, 15, 16 maybe detection channels. Not so impressive. But thing is, and this is our goal, these techniques can be combined. and actually the losses are not multiplied, but by just, they add up. And the number of channels actually multiplies. So if we, bluntly speaking, if we take this guy and put after that guy, we now have 20 times 16 channels. We have hundreds of detection channels, and we have other tricks in our sleeve. Let's say you can use modification of the detector and measure the same state under different conditions of the detectors. For example, you can modulate efficiency of the detector, and at the end, you can have hopefully thousands of detection channels, at least partially independent, and basically we will go to the regime of mesoscopic quantum detection and in sense of number of photons. So, but back to what we are more interested here, so quantum state reconstruction and the corresponding methods behind this technique. For photon number resolving detection, we end with detection statistics, which is not the same as photon statistics, at least because detection statistic is finite, but photon statistic is infinitely large. I mean, there is infinite number of elements. So this is at least this difference is obvious immediately. And now the question is how we can compute this from the detection statistics. Let's try basically all the basic techniques we already mentioned. So we can try direct inverse. It's again, I mean, there is again, I mean, theoretically linear relation between the detection statistics C and photon statistics P. So we can make an inverse. And again, this is really the worst method we can use here, especially because it's heavily underdetermined, and as a result, we will get negative probability artifacts. We will have large variances. We will have very poor agreement between the reconstructed photon statistics and the original photon statistics. By the way, all these are numerical simulations, so we know what is the original ground truth, and we can compare. We can also use maximum likelihood, which is state of the art in this field. It produces much nicer results. It produces physically sound solutions, but it's very slow, which we can live with this in principle. But there is a problem. The main issue here is the overfitting. I mean, the maximum likelihood reconstruction, because it works now only for a vector of real numbers, positive numbers, so it reduces to so-called expectation maximization algorithm. This is iterative algorithm, and we have to stop this algorithm somewhere, early stop. And thing is that we don't know where, so typically we, let's say, assume that if the distance between n and n plus 1 iteration is smaller than machine precision, there is no point to go further, and we will stop our process. Thing is that with increasing number of iterations, the reconstruction goes wild. The variance is increasing. The solution has tendency to go to more sparse states with some photon probabilities more or less almost zero, even if the original state has more or less smooth photon statistics and so on. And the reason behind this behavior is that maximum likelihood has some biases. I mean, it's biased estimator. And especially for a small number of data, there is strong bias to more pure states. And also there is a bias to sparsity. Actually, this is very interesting, and this is very interesting paper here. It can be shown that any inverse method which incorporate the assumption of positivity has some, at least small bias to sparse solutions. So it's actually compressed sensing. You get compressed sensing just assuming your solution is positive, a little bit. Okay, we need to pick a unique solution, and we need to fight with these inherent biases. Okay, what about entropic regularization? This is exactly opposite. It makes exactly opposite bias, and it's a regularization which can help us to pick the unique solution. So we developed maximum likelihood, maximum entropy. We call it EME, like expectation maximization entropy algorithm. It doesn't overfit. It produces order of magnitude more accurate reconstructions, and it's 2 or 3 order of magnitude faster. All these sort of performance figures are averaged over many various quantum states, over many various photon statistics. So if you are interested, there is implementation is actually quite short Python code. And of course, using this, we can reconstruct really accurately large quantum states, classical as well as non-classical, and I would say this is probably the most accurate reconstruction algorithm for processing data from photon number resolving detectors. Okay, we are back to our map. And now, we have the case where the number of projection is same as the quorum, as the minimum needed for the exact full quantum state reconstruction. What do you think? With the number of measurement equals to quorum, do we get the perfect quantum state reconstruction? And a subsequent question, if yes, then basically there is no point of having more measurement projections than the quorum. And yeah, I mean, yeah, I showed you the next slide. So anyway, the answer is no. I mean, we would get the perfect quantum state reconstruction in the case we have infinitely many measurement runs. But in a real case, there are still errors even in full quantum state reconstruction with the quorum. And this is slightly counterintuitive. We can get better results, small error, with more measurement projections than is actually required for quantum state tomography. So how to compare these cases? Let's say we have 2 measurement schemes with the same number of quantum resources, same number of state copies. This is important. And one of them has the quorum. The other measurement scheme has higher number of measurement projections. And okay, we probably needs to be more precise. We need some quantity to evaluate the performance of these measurement schemes. So, how to evaluate the error of quantum state reconstruction? I mean, it's quite easy. We have ideal quantum state. We can make a measurement using some measurement scheme and reconstruct the measured quantum state. It of course depends on how many copies we use. And we can compute some distance between these two states, for example, Hilbert-Schmidt distance. And I mean, this would be error for a single quantum state. So now we need to average over all possible quantum states in the system. This is this averaging. Statistically, we know that this quantity will scale with the number of copies of the state as 1/n. But we need sort of error which characterize the performance for number of measurement projections. So compare different schemes, not different number of state copies. So we simply multiply this error by the number of state copies, and now, at least in the sense of scaling, it doesn't depend on n. It only depends on the number of measurement projections. Okay, what is the minimum of this guy we can get? What is the minimum error? What is the bound for this error? And this can be answered very nicely by something termed quantum tomographic transfer function, which is long name, but actually it's just the Kramer bound, again averaged over all states. In this case, over pure states, because we are really looking for the minimum possible error. And okay. Some examples. So let's say we have single qubit, very simple system, and we will measure the quantum state of single qubit using the minimum symmetric informational complete measurement with only 4 measurement projections. This is the minimum we can do. Then the bound for this error is 4. Okay, this is a little bit cryptic number. It actually means average Hilbert-Schmidt distance or error per a single copy, per a single measurement run, so 4. If we increase the number of projections to 6, so we use Pauli measurement, for example, the bound for this error is 3. And if we going further and increase the number of measurement projections to infinity, we get something we called covariant measurement, and the bound for this error is 2. And it's actually the lowest error we can reach in any tomographic-like quantum state characterization. So, can we reach such low error, actually? We performed some experimental testing. This is the result for a single qubit. And we used 6 projections or 120 projections. Basically, projections to state uniformly distributed across the Bloch sphere of this single qubit. It was optical experiment, so with photons, the degree of freedom or the information, the qubit was encoded to polarization degree of freedom. And you can see that the measured data, the markers more or less agree with the theoretical bounds, which is 3 point something for this scheme and 2.5 for this scheme. So yes, and yeah, important thing is that always we have, I mean, when we compare this point and this point, we have the same number of state copies. So with same quantum resources, we can improve significantly the precision of our measurement with increasing number of measurements. Okay, the same or similar results also for 2 qubits. Now it's a little bit more wider. It's sort of, it's not flat, but these are technicalities. Still, we can see that the error of 400 projection measurement is lower than error of 36 projection measurement. These, let's say, imperfections or irregularities, you can see, for example, this decreasing for lower number of detection events. This is based. This is caused by the maximum likelihood bias towards more pure states. We already mentioned this, and this increase, this error increase is due to the systematic errors. It's important to think that everything we mentioned so far discusses statistical errors, sampling errors, but not experimental deviations we have in real experiments. And by fitting, we can see that these systematic errors are of the order of 10 to minus 5 to 10 to minus 4, so extremely small. And of course, it was quite a pain to reach this accuracy. So the question is how we can control the, in our case, polarization or let's say arbitrary quantum device to this level of precision. I mean, besides the high accuracy, we also need fast operation, because we need to switch between many quantum states, between many measurement projections. So instead of using the common technique of rotating some birefringent elements, some wave plates, we used liquid crystal device consisting of several liquid crystal cells. Basically, it's a material which can change the polarization of light if some voltage is applied. The question is how to find the proper voltages. So how to find the optimum control signals which can make our device, our quantum device, operate as we want. So originally we started with brute force optimization using genetic or evolutionary algorithms, but later we developed something termed bidirectional quantum control, and it's a pretty general way how to optimally control quantum devices, and it uses machine learning. So let's discuss a little bit this concept. Quantum device, which is controlled by some classical control signals, can operate in this direct regime. We set somehow the classical signals. There is some operation, induced operation of the quantum device, and we can characterize the output, for example, using full quantum state tomography. So this is straightforward. Thing is that we need the device in opposite direction. We need the inverse model. We need sort of the specify somehow our target operation, our target quantum state, for example. And we need some model to tell us which are the optimum classical control signals. And analytical or theoretical model for liquid crystals is notorious for lacking accuracy. You can easily get 10–15% of error, which is completely useless for our case. So we need something better. We need probably fitting and interpolating our experimental data of, from the characterization of the device. So we can use a deep neural network. Problem is that during the learning neural network, the loss function, the error of the network, is evaluated at its output, typically. And in our case, it means the error evaluated in the space of classical control signals. But this space is completely arbitrary. You can have 3 voltages, but you can have 6 voltages. And obviously, with more classical signals, the overall error will be larger. But it doesn't, numerically. But it doesn't mean that it's, worse than the device with 3 voltages. Also, the range of the voltages is more or less arbitrary. So, yeah, and also how we can decide if the error in 1 voltage is more serious than the error in the voltage. So basically, this is not ideal solution. What we sort of suggested is making this learning of inverse model sort of unsupervised, like it's not completely unsupervised because this compound model or daisy chain model consists from the pre-trained direct network, which was trained for the experimental data and then was fixed. And only this part is trained now. And the thing is that now the output of the whole network is again quantum object, quantum state or device. So and we have metrics in the space of quantum states which are physically inspired. We have fidelity. We know what they mean and how we can interpret them. And actually, the space of classical control signals now plays the role of latent variables in such a model. So this is our bidirectional quantum control. We can reach full control of, in our case, of liquid crystal polarization modulator. We can prepare arbitrary states and with the fidelity higher than 3 nines. But what I want to present is not these numbers, but actually the concept of bidirectional learning. When we navigate not in the space, we will not navigate and optimize in the space of classical control signals, but actually in the space of quantum objects, quantum states. Okay, thing is, it's still pain. If you need to calibrate somehow your device or use sophisticated workflows for calibrating hundreds or thousands of measurement projections, it's not user-friendly, let's say. such a measurement scheme. So the question is, if we don't need this individual calibration of these measurement projections, maybe we can make them random. Actually, the ultimate limit, the covariant measurement with infinitely number of measurement projections is actually defined as a random measurement scheme. So we have random, infinitely many projections distributed according to Haar measure over the block sphere, let's say, and this is covariant measurement. So what about a finite number of random measurement projections? Can we live with this? Easily? We can very nicely. We have physics tools how to prepare such measurements. Basically, every random scattering process gives us random measurement projections if complemented by some detectors at the output. But the problem is that now the output is random, and we need something to interpret, to encode the measurement results and compute the original quantum state at the input. And this will be, again, machine learning, because this is the most efficient way so far we can have for this. This is just an example of what we can do with this. It's all fiber polarization sensor. So it's basically a device which very quickly and very accurately can measure full polarization states of light at the tip of the fiber. And because the polarization, and it works at single photon level, and because at single photon level, polarization degree of freedom is basically single qubit. You can also think of this like single qubit quantum reconstruction device. Okay, we have input light. We have very short piece of few mode fiber, which plays a role of random media or random measurement. And at the output of this fiber, we have speckle. We have random scattering pattern. And this scattering pattern can be now sampled by detectors. We want single photon resolution, so single photon detectors, but I mean they are quite bulky and we need to use this sensor for microendoscopic tasks. So basically we sample using fiber array, and the signal now is fed to single photon detectors via the fibers in the fiber array. This is the hardware part. And the rest is computational neural network to decode the random photon count distribution back to what is the original polarization state here. If you are interested, we can discuss later afternoon. What is important for this lecture? Okay, some applications, not important now. What is interesting for this lecture is that we have large network now, like huge, which consists of two parts. Hardware part, which is fixed, not updated, and it's random. And computational network, which is updated, which is learned, so it's not random. And it means from the whole structure, from the whole network, only a subset of the connection is actually trained. And of course, now we can discuss the trade-off. It's better to have larger physical fixed scattering part, or it's better to have larger computational neural network part, and so on. And Actually, it touches some concept in machine learning, very interesting concepts. For example, extreme learning machines, ELM. This is basically a huge random network. So basically, it was typically in IT. It's typically implemented as a multiplication by a large random matrix. So it's numerical. In our case, it's hardware, but doesn't matter. It's a projection from the input space of my sort of features, or let's say from my input space to some very large space. And this projection is random. And there is a single tunable layer, so it's not even deep learning, it's just a single layer. And on the top of it, in the original proposal, it's a linear layer. I mean, the goal for ELM was to be trained very quickly. And of course, if you don't have deep neural network, you don't even need back propagation. You don't need stochastic gradient descent. I mean, if you have single linear layer, just a linear regression is sufficient for this, and it can be very, very quick. But okay, this is the original motivation, but for our problem, basically, this is some extreme point. Huge, random, one-layer computation. We are somewhere in the middle. We have medium size, medium complexity hardware and medium complexity deep neural network, few hidden layers. And on the top of it, of course, because the part of this system is really hardware and we use single photons, we also can test in this system, or for this system, we can test how it's sensitive to sampling noise or to single photon, single particle operation. So actually, this, I think, makes nice playground with lots of research possible, and of course, even with some application in extreme sensing. Okay, yeah. Hopefully we are somewhere here and not here. Okay. One last note to this random projection stuff and these huge networks. I mean, do we really know that we are not losing some information during the transmission via such complicated structures, via such huge network, partially random hardware, partially computational network? I mean, how we can evaluate the information we can get through and the information which is lost in principle. And typically for this, especially in statistics, in the area of parameter estimation, for this we typically use Fisher information, which was quite unbelievable sort of to think even that something like Fisher information will be applied for such complicated network structures. But recently there is a result of evaluating Fisher information and its flow during the hardware scattering process, basically scattering of waves, which is exactly what we use in the first part of network. So now this could be applied, and this could tell us if we really have the optimum network for sort of, in our case, transferring the information about the polarization to spatial correlations of intensity, so spatial scattering structure. But I mean, okay, this is only the first part. What with the neural network? And this is even more recent result. This is, I would say, breakthrough, in my opinion. Stefan Rotter developed the idea how to evaluate the flow of fishery information through deep learning or deep neural network. And it, of course, gives us now, I mean, I think this will be extremely rich research field now. And just a sneak peek, for example, for neural networks. I mean, from practical point of view, when you train neural network, you need to stop the training somewhere again, of course. Basically, early stopping. And typically for this, you use another set of data, validation set. You are training on training set, and you have validation data basically to know when to stop before the network sort of starts to overfit. And the main reason for this is because we don't know a priori before the training of the network. We don't know what is the minimum validation error which can be reached. Okay, now with fishery information, we can predict this minimum value. So just from the training data, just from the data we have before the training. So we know when to stop our network just using this concept, without using additional data. Okay, anyway, this was advertisement for Stefan Rotter Group. And okay, we will see. This is we start a new sort of topic here. So let's see how far we can get. The rest will be next lecture. As I said in the beginning of my lecture, we don't always need the full quantum state reconstruction, the full information about the quantum state. Sometimes we are pretty happy to know some particular feature, some particular quantum feature of our state, like could be purity, entropy of the subsystem, some information about entanglement, and this is very important for us typically. And these transformations, by the way, another thing, for example, the bounds for cryptographic keys. Also, it actually, when we compute this, is a function of the whole quantum state, but it's a number. So it's again some quantum feature, how the quantum state performs in particular application. Okay, anyway, all these features are typically nonlinear functions of a quantum state. And we know that deep neural networks are universal approximators under some conditions. So it's quite obvious that we could use deep learning for extracting some quantum features from the data we have. Okay, entanglement. I guess here it's not necessary to stress how important entanglement is for fundamental quantum physics and also for applications. Actually, the applications ranges from quantum communications to even characterizing the phase transition in complex matter, because also here the phase transitions are linked with entanglement and changes in entanglement. Anyway, quantum entanglement reveals as non-local correlations between local subsystems. And of course, obviously, now if we have some local measurements and their correlations, we have some information and we can try to say something about the entanglement in the system. One important note, this is tricky part. If we would like to know the entanglement exactly and fully, like really the whole structure, this problem actually scales in the same way as full quantum state tomography. For more information here, or we can discuss later. Actually now the question is what we can learn from some finite data. First we need some information about how this problem is solved sort of commonly. What is the state of the art, and to have some baseline for the performance of other new methods. And the baseline here is indirect quantum state reconstruction. So basically, we have some measurement and data. We reconstruct the quantum state, and having the full description of the quantum state, we can compute the entanglement. For example, some measures of entanglement like concurrence or mutual information, for example, for large dimensional systems. You can see the entanglement quantification error using maximum likelihood. So basically repeating this process for many states, numerically generated, and evaluating the error of the let's say concurrence in this case with the concurrence of the original ground truth state. And we can plot this error as a function of number of projections. We start with 36 projections, which is the quorum for 2-qubit states. And we decrease the number of projections almost to nothing. And obviously, the error of predicting entanglement or quantifying entanglement is increasing with the decreasing number of measurement projections. Okay, instead, we can train a neural network, deep neural network, which inputs the data for a particular specific measurement scheme and outputs the entanglement. And again, we can evaluate average error over many states and, of course, for different number of measurement projections. And we can see that this deep learning outperforms significantly the state of the art. I mean, it's sort of obvious, or we can expect this, maybe not that much, but we can expect it because in the baseline, we use quantum state reconstruction. So first, from incomplete data, we try to reconstruct the full quantum state, and then we evaluate a single number from this 2x2 matrix. So it's for sure, it's not efficient way how to do this. And the neural network is, in this case, much more efficient. By the way, one note, this is a little bit issue here. Of course, the network here is trained for one particular measurement scheme. So basically, we need different network trained here and different here and different here. The good news is that we train everything on synthetic, numerically simulated data. So it's reasonably fast. and we not making any bias because of inputting experimental data there. It can be done also for higher number of photons. Here is the example or demonstration of quantifying mutual information matrix. It's actually 3 independent numbers characterizing all pairwise correlation and entanglement between 3 parties, between 3 qubits, and again, we see this nice performance of neural networks. So this method produces physically sound outputs. Basically, we always get the number with the correct, in the correct range of values of this particle entanglement measure. It's trained on simulated data. We tested this up to 5 qubit generic state, so without no assumption about the structure, which is at least some attempt to make it scalable. And it also works nicely for experimental data, but again, experiment is a little bit beyond the topic or scope of this lecture, so we can discuss later. But very interesting thing I have to mention, and this is actually there is a huge amount of, or huge number of applications of neural networks and in general machine learning in quantum physics. And typically these solutions or typically these applications study only 1 particle dimension, like 2 qubit system or 100 qubit system and so on, but 1 fixed sort of dimension. And thing is, when you try to generate an arbitrary random quantum states in an arbitrary dimension, you very quickly hit the problem of so-called concentration. So basically, your states start to be concentrated in some part of the system, and I mean it can be nicely demonstrated if you compute some quantity like entanglement, in this case mutual information. You can see that originally the mutual information was distributed almost over the whole range between 0 and 1 for 2 qubits, but same method give us for 4 qubits only partial coverage of the whole range. So I am just saying that we haven't solved even a generation of synthetic data for machine learning applications in quantum physics. So definitely, I suggest to try to see, to have some insight what is behind the training and application of artificial intelligence in physics and especially in quantum physics. Okay, and that's all for today. Thank you very much. Any question now, or we can leave it after? Sorry. Mm-hmm. You have like a kind of estimation of how many loops you have to put in this new setup? Okay. So the question is basically, what about losses and other imperfections in time multiplexing? for photon number resolving detection. And if I can sort of estimate what can be reached. I mean, this is a very good question. The losses are really the restrictive, highly restrictive in a spatial, in time multiplexing, because obviously, I mean, the losses of this whole part sort of applies. This loss applies several times in each round trip. And this is exactly why we use free space optics and not fiber optics, because with fiber optics there is lots of losses at fiber interconnections and so on. Also, we made this electro-optic switching very fast, so we need only around 15 or something like 15 meters of free space propagation, and we use extremely high reflective mirrors. Actually, I would say, frankly, that there are larger problems in this scheme, for example, the stability, because, of course, this is not easy to keep sort of stable for 20 meter or 15 meter delay line times 16 round trips. Anyway, this is my answer. We were able to get 15 or 16 round trips. For more, the stability and losses are quite prohibitive. Thank you very much.